Okay, so in this video we will speak about the diffusion equation, and the diffusion equation again is a second order partial differential equation. And so what we will briefly cover within this video will firstly be how to get to the diffusion equation. Second, I will then try to reach the diffusion equation using the concept of a biased random walk, and it is through the random walk that I will generate a difference equation. We will convert it, then taking the suitable limits into a partial differential equation, and then of course later we will proceed with trying to find solutions for the problem. So one thing I will comment on before is that in sometimes the diffusion equation, it can also resemble the heat equation, and the reason is pretty simple, because here we look at particle flux, the flux of particles through space, and in the heat equation we look at the heat flux. And so in some sense it can turn out that they have a similar structure, but because it's more intuitive to deal with the particle diffusion equation or physical particles, we will look at it in the same form. So I will highlight out the problem to you. We have some space. For now, we can consider the three-dimensional space, and we are given that initially there is, so suppose there are n particles, the particle number is conserved, and they are distributed throughout the space in some fashion, and at each point, so some vector r denotes the location of each point, and we know the density of particles of at time t equals 0. So we are given rho will now denote the density of particles. It's the number density, not the mass density, at this vector r, and in general we want to find how rho of r comma t looks like, and that's what the problem is all about. So this is an initial initial condition which will determine the value of this rho at a given later time. So what we want to look at is how these particles move, and so the most basic model for how the particles should move is given by Fick's law of diffusion, and what Fick's law says is this: J is the particle flux, or whatever. It looks like a current density. It's like a particle flux density. So, and D, and this is the negative gradient of the existing distribution of particles in something. So if I consider a volume where there are lots of particles, and suppose they are very dense towards the center and they smooth out further and they separate out further. So the gradient of this concentration of particles is in some sense inverse. And what Fick's law says is that how the particles will move, that is the particle flux, is simply going to be in the direction opposite to the gradient and proportional to the gradient, and the proportionality constant is d, and so d will roughly determine how quickly or how well these particles will diffuse. But this is what we can add something to this form of J, because in most cases it is not so that particles are free to move as they like, right? So I'll just clean this and then we'll talk about it. So suppose I have a stream where there is already the medium behind already has some speed, say call it V. And again, now if I leave in a bunch of particles, the way these particles will drift around is not only influenced by their concentration or the concentration gradient, it will also be influenced by this V. And so the term we add to this will be, and this may remind you of the rho V that you sometimes write in electrodynamics, J equals rho V, but this is different from this. So best not to confuse the two. So this this is the model we will use for J, and now we will try to convert J somehow into rho, and we will obtain the we'll obtain an equation for rho somehow, and that will be that will be done by simply writing the continuity equation, correct? Because what the continuity equation simply says is the following. Correct? That's the continuity equation, and that's obviously, in case you haven't seen it in this form before, it's not too tough to derive at all. I can just, so what you can, how you can get to that is just consider a small volume, say tau, and just conserve the number of particles. So the flux of particles moving out will be equal to the change in the number of particles inside, and you will once have to probably apply the divergence rule, if I remember correctly. Yeah, that's, and you will immediately read. So I will not go into that. But anyway, so since we have this, we can immediately just substitute J in, and so we have, and I will take this del rho by del t to the other side, or in fact I'll take this to the other side and bring del rho by del t here. Right. So now what's important to notice is that this V, the speed of the stream, it doesn't necessarily have to be uniform, or it doesn't have to be a streamline flow, as they say in fluid mechanics. It could in general be some velocity field, a vector field. It could be some, and so, and the same, a similar thing can be said for D as well. D is diffusion constant or whatever they call it. It doesn't have to be isotropic. The medium can be anisotropic, correct? So for now I will not take D out of this, but what I can surely do is I can send the minus sign inside, and this becomes minus, and so we will have minus, and everywhere, in case I don't mention it, rho is for now. I can, although for now I just want to formally open up this expression, and then later we will ultimately, if we want to even have a decent chance at solving this, we will have to assume that D is that the medium is isotropic, so D is constant, as well as assume that V is some constant uniform speed in some velocity in some direction. But for now, let's just keep it as general as possible. So to expand this, obviously we can apply the product rule. Uh, uh, that will be this, and this term will somehow uh, Okay, no. Yeah. This is the this Nabla square denotes the Laplace. And so putting everything together, I think we will get something like this. Erase this part as well. Okay, no. Minus minus v minus v okay, and so that's in 3 or in some number of dimensions. That's the general form of this partial differential equation. Some comments I will make right now about D, something just struck me is that D also may depend on the other parameters of the system. For instance, for the ideal gas, there is a famous result, and that is that D is of this form. V is the mean speed or whatever the thing that becomes. So this is the elementary form for this, and lambda is the mean freedom. But anyway, so this is the form of the equation, and what we will now assume is firstly we will assume this. Secondly, we will also assume that so the medium is isotropic, and I would also like V to be a constant so that this stuff simplifies out rather than having some divergence plus arbitrary function. I will assume V is some V naught, some constant, right? But we will come back to this. For now, what I want to do is I want to come to this form where, okay, I have cut this out and I have cut this out. I want to come to this same form using difference equation, and for that we will look at a random walk. So what a random walk involves is so this is the one dimensional random walk, and it's as follows. So you have a starting point. So a person starts at a starting point, say person, and the with some probability, some known probability, we will have to know the probability. Sorry. With some probability, say P, she or he moves forward. With Q, she moves backward. And at every step, it is a completely random process as to which one will happen with these fixed probabilities, P and Q. And ultimately, we look for what's the distance covered, what's the mean squared distance, and so on. So, but I'm pretty sure you're already familiar with this. Now, how does a random walk somehow translate to a diffusion equation, right? So, the first thing that we will do now onwards, is that we will not look at this rho as a function of identity. What we will do is we will already divide, since all these particles are identical within the we assume that all the particles are identical. So I can simply divide this through by n, the total number of particles, and somehow get something like uh, a probability distribution sort of thing. I will correct this, which I will denote as P of capital Q because small p is already used up here. Anyways, so we will now look at one particle and then multiply everything by n when needed to figure out what's going on with n particles. So we can now look at one particle, and that immediately reminds us that we can use a random walk, because a particle is in some sense it will not be a completely unbiased movement because p's and q's are not equal, but it will be a random movement, like random at least to the degree that these we can use these probabilities, right? So in order to go about that, I will first look at a one-dimensional case. I will draw a big or whatever. I can mark lattice points. I shouldn't draw the line. I'm not sure how clear that will be, but I'll draw a few lattice points, and suppose this is 0 and the particle starts here. Okay. And now the particle moves to can take a step to the right with probability p. It can take a step to the left with probability q. And for the sake of dimension, I will say that this step length that the particle can take is L, and the particle makes one step in some characteristic or whatever, some unit time, and I will call that time as say capital T. So in each interval of t, the particle takes a step to the right or to the left with this p's and q's, and the length of the step is L. And so we want to know in some sense what will be the probability after n steps, and n steps will translate to time elapsed of nt, and in that time nt what's the displacement of the particle or what's the mean square displacement and so on. In general we want the entire PDF of those of what happens later, and later then we can we can either take out moments, so on, figure out later whether making that assumption that everything is random is even justified. It will turn out it is. So again, so let's start with this. So at some time, say nt, or okay, I am looking. So I will denote the probability that it is at some length, say nl, and at some time mt as this. So after, so it is at some distance nl after an elapsed time of mt, and we can straight away say that m is more than n, because I started everything where it was at 0 and at time t0, right? Anyways, so I want to arrive at a difference equation or a recurrence relation, however you look at it, for n and m in terms of n minus 1 and m minus 1. So if it is here at this point nl, this must be n minus 1. This is the positive x-axis, and that means that 1 unit time later it was either over here or it was over here, correct? So that would mean this is equivalent to, and the probability that it was here is actually p, because p is a probability with which if it was here it would have moved to the right, and so I write this as small p times or it could have been to the right and moved to the left with this probability q. N plus 1 L. I'll just remove this. Right? So I've got a sort of decent looking relation between Pn and the previous uh, at m minus 1 and n minus 1. Now, as we do in converting the difference equation into a partial differential equation, we will take appropriate limits, and those will involve sending this lattice constant to, or whatever you call it, that L to 0, this times this step length or whatever. I mean, whatever the characteristic time of taking a step, I will send that as well to 0, and then we will look at what can be done. And so to do that, I want to, so again, taking hints from the fact that in the equation I had previously derived, there was a term del rho by del t. So I want something like del p by del t here. And so for that reason I will subtract a term which will correspond to okay, let's just go ahead and do that. P of n small p times okay, and I had subtracted p of nl and minus 1 minus p of nl and minus 1. Okay, and divided by t, and this also is multiplied by t inverse. And we were simplifying this because this simply became del p over del t. Good. Now, since this is multiplied by something like p plus q is 1. One must remember that, because p is the probability to go to the right, q is that for the left, and therefore in all p plus q must be 1. So I will rewrite this as minus p times minus q times p of whatever, and then again the same thing. And now we simplify as p times minus 10 minus of that minus p of, and this term I have done it for the p's, and this will simply become minus p times minus small p times this. So n and n minus 1 is separated by l, and so I will write it as at nl. Right, I will consider this point. And similarly, what we will get over here, using this q, this and this, we will get minus q times l times del p over at n. And we simplify the addition of this further. Okay. So we had minus p times del p over del at n plus at n. And so what I want to do is convert this into, since I had something like this, I want to convert this into symmetric and anti-symmetric parts in P and Q. So then I can club together these derivatives and we can proceed somewhere, right? So wait, am I doing the right thing? No, this is at n plus 1. This is at n plus 1 because Q involved. I hope to see that. Okay, no, these will be in opposite. So n minus 1 L minus P times NL. So that will have a minus sign. And Q times that for n plus 1 and minus n. So apologies. This is the correct expression. But anyways, so that the thing I just said before that still holds. I will write P as P plus Q over 2 plus P minus Q over 2 and Q as P plus Q over 2 minus P minus Q over 2. Or if you say I can make it minus Q minus Q, right? So this becomes minus P times P plus Q over 2 del P by del S at n minus, oh sorry, P, P minus Q over 2, and this was all multiplied by L. Please don't forget that. When we had taken the first derivative, we had multiplied by L. So I will still continue this inside part irrespective of this. Del P by del S at n, and now we have this plus sign P plus Q over 2 times del P by del S at n plus 1 L. But and I have a Q minus P over 2, right? Yeah, and Q minus P I will write as minus of P minus Q, just like this, and so it will become minus of P minus over 2 del P by del S at Ns. I'll take this part out. At Ns. And these P plus Q's now can be added together. P plus Q over 2 times. So now there is a difference of n plus 1L minus that at n minus 1L. So it will be del P by del X at n plus 1 L del P by del X at NL. And what's this? This is simply L times the second. We take another derivative. So this will be L times del square P over del X. And we also have these additive terms, which will be P plus Q over 2 times simply del P by del, right? L del P by or whatever. The L is still also, right? This will remain in the first order. So yeah, now that's fine. And this is P minus Q, sorry, P minus Q. So I will clear this and write it back. So what we had last time was something like this, del P by del P. This was equal to L square times del square, L square over T, because we had this del X square, and yeah, times P plus Q, Yeah, p plus q over 2 minus uh, q minus p over 2. It was p minus q added, so I subtracted minus q minus q. And del p by del x. P del x times L over T. Correct? And this looks a lot like that. Now, all we have to do is write this L square over 2T times P plus Q. We define this as this new letter D. And what that tells you is that there is always going to be diffusion because P plus Q is always 1. Correct? So L square over 2T is 2 times this whatever characteristic time is capital D. And there is also this term which is something like, and this has the physical dimensions of a velocity, so you know it's in agreement with that, and so I will write this as v. And what you should notice is that when q minus p is 0, that is when it is an unbiased random walk, when it is equally probable that the particle moves to the right or to the left, that time this v is 0, so it corresponds to no external velocity field, if you say so. And the reason why I wrote p minus q over 2 as minus times this is because I wanted it to resemble that, right? And actually this v is just a number, so it doesn't make much of a difference, but I wanted it to resemble the equation we just. And so we'll make these whatever this. We'll this 1 by t I wrote by mistake, but this is the general form. And I will now convert this by sending him all the d's and the v's, and so the final equation we will get by is something like this. And in one dimension, this is the cleanest form of the diffusion equation. Correct. So I will solve this for one dimension, and then for we will first solve it for one dimension, and we can later extend it to any number of dimensions. And the reason for that is that since the space is isotropic, we don't care how it moves. I mean, it's the same thing whether it moves alongside the x-axis, the y-axis, the z-axis. Don't it? I may have got the directions wrong, but anyways, we will now go ahead and try to solve this.